Hi everyone, we are Group 13. Our design project targets an ongoing concern for humanity, which is carbon emission control.
Carbon dioxide concentration in the atmosphere has increased exponentially as a result of an increasing dependency on fossil fuel, which is mainly driven by the power generation sector. Unfortunately, the current social structure cannot afford any rapid reduction in energy consumption, or even the transition towards sustainable energy resources is now undergoing. The time frame of such transition could take up to decades to complete, thus stimulating the development of the carbon capture storage, or CCS. CCS helps in reducing the carbon emission while allowing industries to make little to no reduction on power consumption.
However, waste streams with low CO2 concentration can be both expensive and difficult to capture and store. That is why chemical looping combustion, also known as CLC, is being considered more widely as an indispensable process to facilitate a better CCS process. CLC allows for conversion of fuels with inherent CO2 separations. Instead of using cryogenic air separation, redox reactions of the oxygen carriers are utilized to facilitate a more efficient conversion of CO2. As shown from the schematics, the oxygen carrier is oxidized in the air reactor, so oxygen can be provided for the combustion taking place in the fuel reactor. With that, the effluent from the fuel reactor contains mostly pure CO2 and stream can undergo further CCS processes. Among the many CLC units designed, the 1 MW Darmstadt setup consisting of two interconnected fluidized bed reactors were chosen to be further investigated within this project. The oxygen carrier plays an important role within the CLC system since it enables the oxygen and heat transfer from AR to FR. An iron-based material, aluminite, was chosen to be the carrier given its low toxicity and good reactivity.
There are mainly four constraints and three success criteria that need to be taken into consideration in order to optimize the design of an industrial-scale CLC unit. For the constraint, we first need a generation of at least 1 MW of thermal power, which should be under a moderate-sized power generation plant and have a steady output. Second, the operation must be under safety condition, which means the operating temperature must be lower than 1600 Kelvin and the operating pressure must be lower than 10 bar. After that, the operation must achieve 90% of fuel conversion to carbon dioxide. Finally, the system must meet health and environmental protocol such as reusing and recycling the waste oxygen carrier. As for the success criteria, we first have to maintain design model within the constraints while assessing the feasibility. That is to say, we must achieve a model discrepancy of less than 5% of all species conversions. Second, the model must align with the published experimental data. At last, the operating cost must be optimized. For instance, the operating cost should be lower than $97 per megawatt hour generated.
The CLC model consists of three main phenomena: hydrodynamics, mass balance, and energy balance. The model is largely based on the dynamic mathematical model proposed by Kormos and Chisolita, which uses the operating and design parameters based on the 1 MW CLC unit operated at the Technical University of Darmstadt. The hydrodynamics model is solved mainly in an axial direction with horizontal separation between the core region and the wall layer using empirical correlations. The fluidized bed dynamics depend primarily on the gas flow rates, the properties of solid and gas, and the column geometry. The model determines the solid fraction, solid circulation rate, and the pressure drop throughout the column. The steady-state mass balance on the gaseous components follow a plug-flow reactor model. The solid mass balance is modeled as a CSTR between the two columns under the assumption that fluidization leads to vigorous mixing. The kinetics of redox reactions are implemented as a function of solid fraction and solid circulation rate obtained from the hydrodynamics model. The mass balance model determines the flow rates and the convergence of solid and gas species. The energy balance model consists of three sections: gas energy balance, particle energy balance, and heat transfer. The gas energy balance uses a plug flow assumption, and the temperature profile is calculated as a function of heat of reactions, particle to gas heat transfer, and flow rates of the gas species. The particle energy balance is modeled as a CSTR between the two columns, where the oxygen carrier acts as a heat transporter by circulating between the two reactors. The particle temperature is a function of heat transfers between the particle to gas and particle to wall. These heat transfers are determined by three different mechanisms: convection between the gas phase and the oxygen carrier particles, convection or conduction with the moving particle phase, and radiation. The developed CLC model is a system of partial differential equations. The IPOPT nonlinear solver was selected to solve this complex system, and the Python PyOMO library was used to implement the model equations. By using this library, the model can be defined as an optimization problem by setting variables as constraints. Simply adding an objective function allows us to solve the optimization of the model.
For validation purposes, data obtained by Vienna UT was compared with the output of the model, as that is the only available data obtained that represents a CLC system with Illumini being the oxygen carrier. All operating conditions and model initializations have been revised to match with the Vienna UT setup. Note that the model is only adjusted to match Vienna setup in the validation phase. All profiles and parameters are reverted back to the Darmstadt setup once data validation has been completed. Hence, it is safe to assume that all findings within other sections of the project were based off the Darmstadt model. Fuel conversion versus input fuel powers relationship of the model simulation has been demonstrated here compared with the literature. As shown, the model has achieved a similar trend as the experimental data provided by Vienna UT and has obtained an average difference margin of 3.13% and 19.14% for H2 and CO conversion respectively. A source of error observed within the model is the solid inventory, as the experimental data obtained by Vienna UT was based off a solid inventory of 70 kg Illumini, while 92 kg is the closest the model could achieve while reaching convergence. To provide more comparison, Babesh Boye University also conducted a similar validation and obtained a deviation of 10% for H2 and 18% for CO conversion respectively. While our model lacks slightly in CO conversion accuracy, a more accurate profile has been obtained for H2.
The three most important profiles have been demonstrated here to provide insights into both reactors in regards of their pressure, flow rate, and temperature. Fuel reactor experiences a turbulent bed in the initial segment of 0 to 2 meters, then enters fast fluidization afterwards, while air reactor remains in fast fluidization constantly. This phenomenon is well reflected where the acceleration of the superficial gas velocity slows down and approaches terminal velocity after entering the fast fluidization phase. Also, due to the fact that less solids are present within the fluidization phase, there is less pressure drop after 2 meters in fuel reactor. Similarly, for flow rate profile, N2 is an inner species of the system, while oxygen gets packed into oxygen carrier as it flows upwards within the air reactor. The oxidized carrier then enters the bottom of the fuel reactor, where reduction reactions happens to convert fuel into CO2. This is also supported by the temperature profile, as the oxidation reaction taking place within air reactor is exothermic, while the 3 reduction reactions taking place in fuel reactor is endothermic. However, it's important to know that within the fuel reactor, the temperature drops until it reaches a plateau, where the temperature must be maintained to ensure a sufficient reaction kinetics.
A sensitivity analysis has been conducted to observe the effect of the variables on the model. 5 variables from the validated model were chosen with their corresponding sweeping range. For each attempt, one variable was changed and all other variables were set as the standard condition. Once the results were plotted, it was further analyzed by relating the change in species conversion over the change in variable. As shown in the table, it can be noted that omega incurs the biggest impact on conversion. A change in omega by 10% would inflict a change of 16.32% in CO conversion.
Optimization has been performed to minimize the cost of the model. As defined in previous sections, the constraints of the optimization are that the total generated fuel power must be larger than 1 megawatt, and the carbon dioxide purity must exceed 95%. The optimization of the model is mainly achieved by 2 steps. First, fix the oxygen carrier to fuel ratio, or omega, and then fix the air to fuel ratio, or lambda. That is to say, omega is relaxed to perform the first step of optimization, and then lambda is relaxed to run the second step of optimization based on the result from the first step. The reason why optimization process is separated into 2 steps is that if both omega and lambda are relaxed at the same time, the result will not converge. After these 2 steps, the operating cost is about 38% lower while remaining a high conversion of carbon monoxide, hydrogen, and methane. And the power generated is even higher, which becomes to 1.117 megawatt.
The project also makes meaningful societal impacts as it optimized for operating costs that involves energy generation, gas preheating, oxygen carrier replenishment, in which making it more likely to be adopted by different industries, and it calculates the capital costs of building a real-life CLC system as the one modeled. It also promotes carbon footprint reduction by providing a feasible CLC solution towards a better CCS system, and it evaluates the end-of-life oxygen carrier recycling program as the system will generate zero waste. And after all, a safety analysis has been conducted, which the risks and effects are identified with their corresponding preventative actions to promote safer operating environment for the CLC systems through the aspect of mass flow rate, temperature, and pressure.
Overall, the CLC model was developed using the Python Pyomo library based on the 1 megawatt Darmstadt unit. The model validation was through comparing the model results with the published experimental results. While the H2 conversion profile aligns with the published experimental data, deviations were observed in the CO conversion profile. An optimization study was performed to minimize the operating cost of the model. For the recommendation to improve the model, the discrepancy between the model results and the experimental results could be reduced by taking a more in-depth consideration of the CLC unit geometry, as well as the horizontal fluid dynamics and heat transfer mechanisms. That is the end of our presentation. We are hoping to gain personal knowledge as well as make a meaningful contribution to the world with this design project. Thank you all for listening. The references that are associated with the literature review are located here.